Alright guys, this video is about the last couple of slides of chapter 11. We started the phase diagram of water on Wednesday, and let's just do a brief review. Here this slide shows you the phase diagram of water, and here again I need you guys to understand some important things. The three regions of the diagram, okay? Solid and liquid and the gas. Three different regions represent the three different phases. And the three lines. The lines, okay, between the solid phase and the liquid phase. So this line here, okay. So this line represents the equilibrium between the solid phase and the liquid phase. And if you cross this line by going from solid phase to liquid phase, the name of the phase change would be melting. All right, and if you go the opposite way from liquid phase to solid phase, this is gonna be freezing. Okay, now the second line is between the liquid phase and gas phase. Again, it represents the equilibrium between the liquid phase and gas phase. If you cross this line by going from liquid phase to gas phase, then the name of the phase change would be evaporation. And if you go opposite way, the name of the phase change would be condensation. The last line is between the solid phase and the gas phase, okay? Represent the equilibrium between the solid phase and the gas phase. Again, if you go across the line from solid phase to gas phase, this is the sublimation. And then if you go opposite way, then this process is the deposition. 2 points, critical points, and triple point. Critical point means if you increase the temperature, okay, above this point. Meanwhile, if you increase the pressure above this point, then you see there's no difference between the liquid phase and the gas phase. You would not be able to tell the difference between these two. Remember the video I showed you about the water, how water looks like above the critical point. It's homogeneous. Okay, you cannot tell which part is a liquid, which part is a gas. All right, so this is a critical point. Triple point represents the equilibrium among three phases. So at this point, you see solid, liquid, and gas phases. Remember the video? You see the solid ice. Okay, you see the ice, and you see the water reach the boiling point. That tells you that you see the three phases at this particular point. Okay, so these are the important things that I need you to understand. Now, let's see one more example. The phase diagram of carbon dioxide. As you can see from this picture, it has a similar pattern as the phase diagram of water. Solid right here, and the liquid right here, and this phase is gas phase. I have a important question for you to think. The solid ice, dry ice, will turn to gas at room temperature at 1 atmospheric pressure, right? You saw that. You can buy dry ice from Kroger if you want. But the question is why? Remember, we are talking about the phase change at 1 atmospheric pressure. So you would start from here. And when you look at the temperature, dry ice is quite cold, okay? So you are looking at the very low temperature, so you start from here and you move to the room temperature without changing the pressure. So you are moving along this purple line. Okay, you can move forward until you reach the room temperature. And when you move along this purple line, you cross the line between the solid phase and gas phase. That tells you see the phase change, and that phase change is sublimation. And that is the reason. See, here is the phase diagram can tell us some important properties of the materials you are studying. Okay, and so that is how useful the phase diagram to our science. So this is a carbon dioxide. Now let's do some practice. Practice problem 1. Okay, let's do this together. Here's the question. What process occurs from A to B on this phase diagram? Now, let's take a look at this picture. I have 3 question marks for you. And I expect you to know which area, which region is solid phase, which region is a liquid phase, which region is gas phase. Apparently, based on what we learned in the previous 2 slides, we know that this area is solid phase, and this one is a liquid, and this one is a gas phase. Okay. Now, once you assign the 3 regions, you take a closer look about the phase change. You move from A to B. Pressure is not changing because, pressure is right here. It's always here. But you change the temperature. When you go from A to B, you cross the line between the solid phase and the gas phase. That tells you, okay, the name of the phase change is sublimation. Now here is the information we can get from this picture. Now let's take a look at this 5 answers. Now A, temperature increase. Well, this is true because when you go from A to B, temperature indeed is increasing. Phase change from solid to liquid. And this is not true because you are going from solid to gas. So A is not the right answer. B, no change in temperature. Well, this is absolutely not true because temperature is increasing. So B is not right. C, increasing temperature while phase change from liquid to vapor. Well, temperature is increasing, but the phase change is not from liquid to vapor. It's from solid to gas, okay, or vapor. So C is not right. D, increased temperature. Now, no phase change. That's no. We see the sublimation. Okay, so D is not right. All right, the only choice looks like it's E. But is that correct? Increasing temperature with a phase change from solid to vapor. This is right. Okay, so this is how we use the phase diagram to solve the problems. In order to do that, like I said, you have to have a better, very good, clear understanding about the 3 regions, 3 lines, and 2 points. Now let's go to next question. Okay. Before we work together, I want you to pause this video and try it by yourself. And then, once you finish, you can resume this video and we're going to work together. Alright? Now, let's work on this video, this problem. The question is, in the phase diagram shown below, which of the following correctly describes the process from point B to point C? Now again, solid phase, liquid phase, and gas phase. So here, if I don't label those phases for you, I expect you to know how to label them. Now you go from B to C. It looks like when you go from this B point to C point, temperature is not changing. It's always this much. But you are changing the pressure. You are increasing the pressure. Okay, so this is the idea that you need to have once you look at this, when you analyze this picture. Now A, evaporation with no change in temperature. Well, no change in temperature, this is right, but is that an evaporation? From gas phase to liquid phase, this is condensation, so A is not right. B, evaporation with an increase in temperature and pressure. Well, when you look at this, pressure is increasing, okay, but are we changing the temperature? Absolutely not, okay, so B is not quite right. And C, deposition with an increasing in pressure. Well, pressure is increasing, but is that a deposition? Like we just said, that from the gas phase to liquid phase, this is condensation, so C is not right. D, condensation with an increase in temperature and pressure. Well, that's not true because temperature is not changing, so D is not right. Alright, so it looks like again the option is C. The only option is C, condensation with no change in temperature. This is correct. Okay, so this is the problem. Now we have one more problem for you to try. Again, I want you to pause this video and try this problem by yourself. And then you resume the video, we're going to work together. Alright, now let's work on this problem. In this diagram, I've already labeled the three phases for you, okay? Solid, liquid, and gas. Now, first question, approximately what is the normal boiling point and melting point of this substance? Remember how we define normal boiling point. Normal boiling point is the temperature a liquid starts boiling at 1 atmospheric pressure. And same thing for melting point. The temperature when a solid starts melting at 1 atmospheric pressure. So the 1 atmospheric pressure is the key information from this question. From this picture, you see that 1 atmospheric pressure is right here, okay? 1 atm. So you start from this point. Now, how do we find out the melting point and the boiling point? Remember, the melting point means you go from solid phase to liquid phase. Okay, so you are talking about the phase change, when you cross this line. Now, the boiling point means you go from liquid phase to gas phase. That means you are talking about the phase change. Sorry about that. On this line. Okay, so how do we identify the normal boiling point and melting point? You start from here, 1 atmospheric pressure. You draw the dashed line, which is parallel to the temperature axis, which means you change the temperature without changing pressure. Now, when this dashed line intercepts this equilibrium line between solid phase and the liquid phase, the corresponding temperature would be the melting point. Okay, so as I can see, it's about 80 Kelvin. All right, now you go further. If this dashed line cross the equilibrium line between the liquid phase and gas phase, the corresponding temperature would be the normal boiling point. And what I can see here is approximately 170 Kelvin. Okay, so this is how we find out the normal boiling point and melting point. Alright, now the second question, what is the physical state of the substance under the following conditions? A. When temperature is 50 K and the pressure is 1.5 atm, what's the state? Solid, liquid, or gas? Okay, let's work on this. Let me change the color of my pen so I can draw it, I can use a different color for this question. 50K. 50K is somewhere here. And 1.5 atm. Well, that is a little bit higher than 1 atm. Now, when you draw the line, okay, 50K and 1.5 atm. Well, it's in a solid region. That means the state of this substance is solid. B. Temperature 150K, pressure 2.5 atm. 2.5 atm, it's a little bit higher than 1.5. 150K, that is somewhere here. And if you draw the line, okay, you will see that the substance is in the liquid phase right here. So it's liquid. C. Temperature 300K and the pressure 0.5 atm. 0.5 atm is here and the 300K is right here. So what you need to do to draw the line, find out the corresponding state. And it's in the gas region, so it's a gas. So here, this is how we use the phase diagram to solve the problems. Now the question is, why do we care about the phase diagram? Well, in science, especially if you are an engineer, if you are doing research in material science or mineralogy, then it's important for you to study the phase diagram, because by having a phase diagram, you can understand the property of the materials. Okay, and here let me give you one example. here this picture shows you the phase diagram of steel with carbon impurity. As you can see, this phase diagram is very complicated, and the different regions represent the different phases of the steel, and also it represents the different percentage of carbon in the steel. And different areas will give you different property, different melting point, different the structure, those kind of things. As you can see, these are the structure and the melting points and the temperature here. Okay, so it's important for us to understand how iron, how steel behave when you have carbon impurity in it. Okay, let me give you one more example. Remember the Titanic. The tragedy happened about 100 years ago, a little bit more than 100 years ago. And at that time, okay, the standard of the steel is not as good as today's the standard. But the steel in Titanic, the construction of the Titanic, when you use the standard at that time, it's quite good. Okay, it was quite good. It's an excellent steel. However, because the steel has in Titanic, when they do the construction, the steel had too much sulfur in it. Okay, because of the sulfur impurity, you have too much sulfur impurity in the steel. It became brittle at low temperature, and that is why when Titanic collide with iceberg, it just break and give just give a big hole and just lead to the tragedy. Okay, I'm not saying that they didn't do the phase diagram. I'm not what I'm trying to say here is if we can have a better phase diagram, have a better analysis of the steel on Titanic, we might be able to avoid this kind of tragedy, right? Because we will know that how that iron with too much sulfur behaves at low temperature and high temperature. Okay, so it's important for you to understand the importance of the phase diagram if you are doing research like material science. Okay, all right. So this is chapter 11, and let me show you a concept map for chapter 11, and you will see this concept map on Blackboard. Okay, if you go to our course website, and if you will see a concept map folder on your left side, and I'm gonna upload those concept maps in that folder. Now let's take a quick look. Like I said, the central part of this chapter is the intermolecular force. Okay, everything is about intermolecular force, and this part, okay, it looks familiar. It tells you which one of the intermolecular forces is a dominant force for a molecule. All right, remember the chart? And at the bottom part of this concept map here, that is another chart we had. It tells you what kind of intermolecular forces exist for a molecule. So here in this map, I combined both of them. All right, now the top part of this concept map, the property of liquids, 4 of them: surface tension, viscosity, vapor pressure, and boiling point. I need you to know how intermolecular forces impact those properties. And based on the vapor pressure, and we had this equation. Remember, we did the calculation to find out the vapor pressure at the different temperature. Okay, so this is an equation that you need to know. And also, based on what we discussed about intermolecular force and the property of liquids, we discussed the phase diagram and the phase change. All right, and I hope this concept map can help you stand higher when you study our course. Okay, it can guide you through the bunch of different concepts and the equations that we talked about in this chapter. Certainly, you can modify, you can revise this concept map to better fit your background. For instance, if you can add something like intermolecular force increase, then how those 4 properties change. Okay, when you have this kind of intermolecular forces change. So try to add things that you like on this concept map and create, or you can even create your own concept map. I believe it will help you. Okay, it is important for us to find out the connections among the different materials in this in college chemistry too, and I hope you guys can try that. Even if you don't like concept map, try it. Okay, you may like it eventually. All right, so this is a concept map of chapter 11, and here the last slide in this video is recommended questions that I highly encourage you to try even if you got more time. And again, you can find out the answers on Blackboard. All right, this is the chapter 11. Thank you.